Hey everyone, welcome to Professor Long's Lectures in Anatomy and Physiology. I'm Professor Bob Long. If you're watching these videos, you're in my Anatomy and Physiology class or you stumbled across them in the internet. Just know these videos are designed for students enrolled in my class at Del Mar College, and I want them to learn the material the way that I'm presenting it so that they are prepared to continue to build upon that knowledge to have greater and greater understanding of the concepts that we cover. Now in the last video we started covering chemistry. We were started on page 10 in my note set, and we went over all the information on page 10 and most of what's on page 11. And I simplified it here. Everything that I talked about is written down there, and it gives you some examples of some atoms that you should try to draw to see if you can predict if they will ionize or not. We're going to continue with the chemistry lectures, and we're going to finish up the next few pages. We are on page 11 now, and that's where we're going to pick up, okay? There are some definitions in the middle of that page, like a hydrogen bond, ionic bond, covalent bond. Look them up, read about them. I discussed ionic and covalent bonds in the last lecture. What I want to start talking is about the difference between organic and inorganic chemistry, get into pH and organic compounds. We have to have this understanding in order to understand some of the more complex physiology we're going to do later on in the semester. So now, let's talk about some chemistry. When we talk about organic and inorganic chemistry, here's what we mean. For organic chemistry and organic compounds, I'm going to abbreviate chemistry as chem for now. Organic chemistry is the chemistry of compounds that contain carbon. Carbon has the atomic symbol C, and hydrogen, which has the atomic symbol H, okay? We also put usually oxygen, which has the atomic symbol O. But we don't have to have oxygen. So in order to be an organic compound or talk about organic chemistry, we're talking about things that have carbon and hydrogen. If it has carbon and it has hydrogen, it's an organic compound. If it's lacking carbon or it's lacking hydrogen, it's not an organic compound. It's called an inorganic compound. In meaning not. So when we talk about inorganic compounds or inorganic chemistry, inorganic chemistry is the chemistry of compounds that lack carbon and or hydrogen. So, if I gave you the chemical formula for something, CH4, methane gas, that is an organic compound because it has a carbon and 4 hydrogens. If I have C2H6, that's an organic compound. It's called ethane gas, and it's got a carbon with 3 hydrogens like this. This is a carbon with 4 bonds. This is a carbon, 2 carbons bound together, and because every carbon, based on the atomic structure last time, can have up to 4 covalent bonds, unless I tell you otherwise, all the other bonds would be with hydrogen. So all I need is carbon and hydrogen. I do not have to have oxygen. Although some people will say it has to have carbon, hydrogen, and oxygen. That is not true. As long as it has carbon and hydrogen, it is an organic compound. Now, what if I gave you this? Oops. CH3OH. That's an alcohol called methanol. It's a methane with an alcohol group. And I replaced one of the hydrogen bonds, one of the covalent bonds with the hydrogen with an oxygen. I could draw the structure of it, but that's not important. But if you see carbon and hydrogen and or oxygen, it's an organic compound. All of these have carbon and hydrogen, so they're organic. If I draw this, calcium chloride, inorganic, no carbon. Is water organic or inorganic? Water is an inorganic compound because it doesn't have any carbon. Is carbon dioxide organic or inorganic? It's considered an inorganic compound because it lacks hydrogen. I have to have both carbon and hydrogen. If I lack one or the other, or both, like sodium chloride or potassium chloride. If there's no carbon and or no hydrogen, it's an inorganic compound. That's all that it means. And by the way, a compound is any molecule or substance that's made up of two or more different atoms. These are two different atoms. It's a compound. These are two different atoms. It's a compound. If I draw this, that's two molecules of oxygen bound together. But it is not a compound because both of the atoms in this substance are the same atom. So in order to be a compound, the substance must consist of two or more different atoms in bonds together. Compound, that's compound, 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 not a compound because all the atoms in the molecule are the same. So, when I talk about organic, I mean carbon and hydrogen, usually oxygen. When I talk about inorganic, no carbon or no hydrogen or neither. Okay? It's that simple. So, anytime you hear me talking about organic compounds, you know they must have carbon and hydrogen. Now, when it comes to us discussing the organic compounds, one of the concepts we have to discuss before I get into the four basic organic compounds that make up the human body are, I want to talk about the pH scale and what acids and bases are. So pay attention here. When we talk about an acid, now, an acid is described as, well, we can talk about pH as being the negative logarithm of the number of hydrogen ions or protons in a solution. And you can memorize that definition. What we want to talk about is this. This is how I want you to understand this. When I talk about an acid, the simple way to think of an acid is any substance that releases hydrogen ions. We can say a hydrogen ion or we can say a proton, that means the same thing, when placed in a solution. So an acid is any substance that releases hydrogen ions when it's placed in solution. What does that mean? Well, first of all, we have to understand what a solution is. And so let me give you that definition and explain that, okay? A solution is my goodness, I'm drawing a blank on how I want to explain this. It is a uniform mixture. I was going to say any, but it's not any. It's a uniform mixture of a solute and a solvent. Which begs the question, what on earth is a solute and what's a solvent? A solute is anything dissolved into a solvent in order to form a solution. Okay, what is a solvent? This is any substance into which a solute is dissolved. So now look, if you read all these definitions in a textbook, they're kind of a circular argument. A solution is a uniform mixture of a solute and a solvent. A solute is anything that gets dissolved into a solvent. A solvent is any substance into which a solute is dissolved. Well, what in the hell does that mean? So I like to simplify things so I can understand it. And while it doesn't always work this way, I just want you to learn it this way for now, and then you can learn the complexities later. So look, let's say I have a beaker full of water, and it is pure water. There's nothing else in it, completely purified water. That is not a solution, because there's nothing mixed in. Now let's say I have some pink or purple Kool-Aid, since I'm using a purple marker here. I have a whole bunch of purple Kool-Aid, some powder, and I sprinkle that powder in here. And those molecules of this powder start to become uniformly distributed so that they get somewhat of an equal distance between each other. And the whole solution becomes uniform in color, so to speak. Purple Kool-Aid. then what I have is a solution. This would be the solute, the stuff that I put into the solvent. The water would be the solvent into which I dissolved the solute. And together they make a solution, a uniform mixture. Now, what if I took a bucket of water and I had some BBs, like you shoot out of a BB gun, and I poured them in there, and the BBs all sank to the bottom like this? Are they uniformly distributed? And the answer is no. So that is not a solution. It's a bunch of BBs sitting in a bucket of water. This is called a solution because the solute becomes uniformly distributed. What that means is, if I take a little sample from this corner, and I take a little sample from this corner or from this spot or any spot in there, it's going to have roughly the same number of solute molecules in that part of the solution. So the solute becomes uniformly distributed or equally distributed throughout, so to speak. So that's what a solution is. Now, knowing what a solution is, you should know the definition of a solution, a solute, and a solvent. What does it mean when I have an acid? Okay, so I take my proverbial beaker full of water and I mix something else in here. I have a solution here that's uniformly distributed. Doesn't matter what the solution is. And I have this little thingy that allows me to stick a probe in here, and it gives me some reading on a screen. And we're going to call that reading its pH. Now, the technical definition of pH is this. It is the negative logarithm of the number of free hydrogen ions, the number of these, floating around in the solution. The negative logarithm of how many of these are floating around in the solution, not attached to any other atoms, but just floating freely in between them, is what we call the pH. Because this course requires a math level 2 or 3, I forget, I don't know how many people really understand what a negative logarithm is. So I'm going to give you a Mr. Long definition, how I try to understand pH. Just for the time being, we can learn the technical definition and try to understand that later. The way I think of pH is this. It is the probability of finding sort of the free hydrogen ions floating in the solution, or adding and subtracting the free hydrogen ions. But it's sort of a kind of a probability. What is the likelihood that when I put this solution in there, it's going to free some hydrogen ions, or it's going to remove some free hydrogen ions? Okay, here's what I mean. Okay. If I measure the pH is going to give me a number somewhere between 0 and 14, or 1 and 14. Although there are things smaller than 1 and higher than 14, but they're pretty rare. But the pH scale is a scale that gives us numbers that go from 1 to 14. And right in the middle would be 7.0. And anything that has a pH lower than 7.0 is said to be an acid. And anything that's higher than 7.0 is said to be a base, or another way to say base is to say alkali. Okay? 7.0 is neither an acid nor a base. Now, what this number tells us is it's going to tell us what is the probability that I'm going to find some free hydrogen ions in solution or not. Sort of. That's not really the way to think of it, but bear with me. Now, these numbers are sort of a negative logarithm, a base 10. So one number is 10 times greater than the other, and it's sort of an exponential thing. And a lot of people struggle with that. So I'm going to simplify it this way. And this is not how the pH scale really works, but it gives you an idea to wrap your brain around. So let's say that when I dip this pH probe into the solution, it tells me that I have 1,000 free hydrogen ions floating around in there. Some pH number that tells me it's acidic. It is an acid because it's already got 1,000 hydrogen ions floating around. Here's what I mean by that. So if I had a group of people walk into this room, let's say 100 guys, and each guy has a basketball under each arm. The basketballs represent hydrogen atoms that are bound to some other substance or molecule, like in water or methane gas or whatnot. If they walk into the room and they release one of those basketballs so that the basketballs are rolling around in the room, not attached to a person, then they're an acid because they're going to release hydrogen ions when they enter the solution. Or let's use beach balls as the example. You ever been to a concert where they're bouncing beach balls all around in the air to entertain themselves in between bands? Those beach balls represent free hydrogen ions. They weren't free when the crowd walked in. There wasn't anything bouncing in the air. But somehow, some way, someone released one and it starts bouncing around. Originally, that hydrogen atom was bound to another molecule. But once it got released, it's a free hydrogen ion bouncing around in a solution. And the pH tells us what's the probability that we're going to see them happening. Here's what I mean. So this substance already has 1,000 hydrogen ions floating around in it. It's an acid. Now what if I take some other substance? I'm going to call this substance X. I don't know what it is. It's some powder. If I sprinkle substance X in here and it starts to get uniformly distributed, but now the number of free hydrogen ions, as it comes in, it releases a few more. Let's say another, I don't know, 300 or 400. Let's just say 300. So now this number has gone up to 1,300 free hydrogen ions. Then I know that this stuff is an acid because when I place it in a solution, whether the solution was acidic or not, if it released some free hydrogen ions, so that now my pH probe is telling me I have more hydrogen ions floating in the solution than before I added the substance, then that substance has to be an acid because as soon as it entered the solution, it released some hydrogen ions. So if we use this example, let's say I have a crowded room and there's like 5 beach balls bouncing around. We're somewhat acidic. I have 100 guys walk in the room, each with a basketball or a beach ball under each arm. And let's say, I don't know, 50 of the guys release a single beach ball. So now there's 50 more beach balls bouncing around the room. Then I know that group of guys belongs to a group called an acid because as soon as they entered the solution, they released some hydrogen ions. They don't have to release them all. If they release any hydrogen ions, they're an acid. Now we're going to talk about the concept of weak and strong acid, so follow along here. This would be a weak acid. The area is closer to 7.0. The further I go away from 7.0, the stronger the acid becomes. These are the strongest acids down here. What does that mean? Well, a weak acid is an acid that releases very few of its hydrogen ions. A strong acid is an acid that releases a whole bunch of its hydrogen ions easily. So, if I go back to the same analogy, I have a group of guys, all wearing blue shirts, all come in with a beach ball under each arm. Let's say that there's 100 of these guys, and let's say 10 of them release one of the beach balls, and 90 of them don't release any. They're still considered an acid, but they would be a very weak acid because only a small percentage of them, or a small number of them, release some hydrogen ions. If I had another 100 guys walk in, and they're in a red shirt, and each one has a beach ball under each arm, and out of those 100 guys, let's say 82 of them release one of the beach balls. Well, now 82%, a high percentage, have released hydrogen ions into the solution. That would be a stronger acid. The stronger the acid, the more easily they release their protons or hydrogen ions into a solution. And the more this pH number will change. Does that make sense? I hope so. Now, let's say I have the same substance here, and I bring in another powder. I have some green powder. Let's call this powder Y. Oops, that green marker doesn't work. Let me get rid of that. I have powder Y. I don't know what it is, but when I take some of this powder and I dump it into this solution and it becomes uniformly distributed, what if, when it walks into the room, so to speak, let's say I bring in 100 guys that are wearing green shirts. They see beach balls bouncing around, and every time one comes by one of them, they grab that beach ball and hold on to it. So instead of 100 beach balls bouncing around the room, now they remove some amount of those beach balls, those hydrogen ions. They literally just sponge them up so that fewer and fewer and fewer beach balls or hydrogen ions are released into the solution freely. Then I know that that substance is a base. One of the ways that we can describe a base is we say that a base is any substance that removes hydrogen ions when placed in solution. So let me erase a little bit of what I've written here. I know I'm getting to the edges of the visible part of our screen, but hopefully you can still see all of this. A base or alkali is any substance that removes hydrogen ions when placed in solution. So when I put substance, that's the green substance, substance Y in here, what if it bounds up this hydrogen ion and this one, and I watch this number drop down to, say, 700 free hydrogen ions floating around in the solution now? I know that substance Y must have pulled some of those hydrogen ions out of solution and holds on to them, so to speak. So I know that substance Y must be a base or alkali. And it's going to have a pH that's greater than 7. The number will tell us if it's an acid or a base, and whether it's a weak acid or strong acid, or a weak base or a strong base. A weak base and a strong base. The lower the number, the stronger the acid. Between 6.9999998 and 1. And if I go from 7.00001 or whatever to 14, then I'm getting basic. And the greater the number, the stronger the base, the more hydrogen ions it will remove. Weak bases remove a smaller number or percentage of the hydrogen ions. Strong bases will remove a high number of hydrogen ions. So for example, let's say I have a crowded room here, and some people are holding on to beach balls, but there's 100 beach balls, hydrogen ions, floating around freely, bouncing off the walls and off of people. They're not bound to anything, they're moving around freely. We call those free hydrogen ions. Let's say I bring in 100 guys wearing a blue shirt, and of those 100 guys, let's say 12 of them grab onto a beach ball and hold it, but the other 88 don't. That would be a weak base. Only a small number of them are removing a small amount of the hydrogen ions. Now what if I brought those same guys in, but now instead of removing a small number, what if, like, say 85 of them grab onto a beach ball? So the number of free beach balls or hydrogen ions reduces massively from 100 to 15. That would be a stronger base. The stronger the base, the more hydrogen it will remove from the solution, the free hydrogen ions. Does that make sense? Now, I know those aren't the best technical definitions, and chemists are going to hate this explanation, as will most biologists. But I don't really care. I want you to understand what I mean when I say an acid or a base. Acid is any solution that releases hydrogen ions when placed in solution. A base is any substance that removes hydrogen ions when it's placed in solution. The pH number will tell us if it's an acid or a base. Anything less than 7 is an acid, anything greater than 7 is a base. The farther away I go from 7.0 down low, the lower the number, the stronger the acid, the more hydrogen ions it's going to release. The further away I go from 7.0 closer to 14, the stronger the base, the more hydrogen ions it will release. Do you follow? I hope so. It's somewhat of a difficult concept, but it's really not that difficult. Now, excuse me. Hopefully you understand that, and you got to play with that until you do. You know, learning A&P and learning information for a class is kind of like getting good at a sport or at dancing or anything that you do. The more often you do it, the better you will get at it. So if you're struggling with anatomy and physiology, you need to keep doing it. Do it till you can't stand it, and do it 5 more times until it's burned into your brain. So write out those definitions, play with the concepts, and try to understand them. Finally, when it comes to this pH thing, one of the things I want to explain to you is, I want to get across to you is this. Let's say I take some different substances. Let's say I take stomach acid, which is a pH of about 1.0 to 1.5. It's really low pH number. Let's say I take tomato juice. I think tomato juice has a pH somewhere around 4.5 or so. Let's say I take, I don't know, what's another? Urine. It has a pH of somewhere around 6.5. I take pure water, which has a pH of 7.0. I take pancreatic juice. Your pancreas is going to release a juice called pancreatic juice. And the pH of that is somewhere around 7.4 to 7.5. And let's say I take a stuff called potassium hydroxide, KOH, and it has a pH of about 10 or so. If I look at this list of substances, and let's say on a test, for example, I put A, or I put this. Let's put some numbers. 1, 2, 3, 4, 5, and 6. I have 6 substances with these pHs. Which of the following substances would be considered acids? And let's say answer choice A says 1, 3, and 4 only. Is that true? Is 4 an acid? And the answer is no. This one's an acid, this one's an acid, and that one's an acid. These are not. So that answer cannot be correct. Let's say answer choice B says 5 and 6 only. Is that correct? And you would say no. Answer choice C might say 4, 5, and 6 only. Are those acids? And the answer is no. Answer choice D might say 1, 2, and 3 only. And that would be your correct answer. So I could write a question that says, which of the following substances would be an acid? Or which of the following substances would be a base? Then that would be your correct answer for base. Which of the following substances is neither an acid nor a base? What if I wrote the question this way? Which of the following substances would release hydrogen ions when placed in solution? These 3, because they are acids. Which of the following substances would remove hydrogen ions when placed in solution? Your 2 bases. Which of the following substances would neither release nor remove hydrogen ions when placed in solution? Neutral pH. Okay. Now, that's one way that I can ask questions and see how much you understand. Okay. What if I asked this question on an exam? Which of the following substances is the strongest acid? Which of the following substances is the weakest acid? Urine. These are not acids, so don't be fooled by the wording. This is the weakest acid. This is the weakest base. This is the strongest base. I hope you understand the way that I could word the questions and help you try to understand the concepts that I'm covering, okay? Now, that's all of our pH stuff. That's all I want you to know about the pH scale and acids and bases. One last definition I have to give you. I dropped my my eraser, so forgive me. One last definition I want to give you, and I want you to understand this, and then we're done with pH, and we have one more chemistry lecture to go over, and then we can move on to the cell. Okay? The definition of a buffer. A buffer is any substance that resists changes in pH. It's any substance that doesn't want to change its pH, no matter what I do to it. So let's say I have a substance here, and I got my pH probe, and it tells me that the pH of this substance is like 7.6, okay? It's a slight base. And let's say I take a really strong acid. Let's say I take hydrochloric acid, HCl, which is stomach acid or bleach, real bleach. The pH is about 1.0 to 1.5, really strong acid. And I add some of that acid in here. I pour a small amount. I should expect this pH to change because this is a pretty strong acid. But if I only add a small amount, and this thing doesn't change its pH. Let's say the pH changes to 7.599999989 or whatever. It barely moved. It's essentially 7.6. Then this is a buffer. It's resisting changes in pH. Now, essentially, sometimes buffers can be overwhelmed because there's only so much of the acid they can absorb. And if I continue to add it, I can overwhelm that. And you'll learn that when you do chemistry and you do titrations with potassium hydroxide and all of this stuff. And there's chemical indicators where it turns that pretty pink or purple color. But anytime a substance resists changes in pH, whether I add an acid or a base, if the pH doesn't move, it's a buffer. Now, the reason this becomes important is because those free protons, those free hydrogen ions, are almost like someone who's super codependent. They have to interact with something, and sometimes they'll interact with other molecules and mess up their functioning. And strong bases can sometimes pull so much hydrogen out that it also messes up other molecules' ability to function. So the pH of a solution has to be just right for certain chemistry to happen within it. Too many hydrogen ions or too few can disrupt the chemistry of other molecules. So understanding pH is somewhat important. And we use a lot of buffers in our body to resist changes in pH. If you drink some pickle juice, you don't want to become too acidic, so your body has some buffers that can neutralize some of that acid. We're going to talk about that as we go on throughout A&P, but that's why the concept of acids and bases and pH are important. Okay? Listen, I hope you learned something. I hope you had as much fun as I did doing this, and do this till you can't stand it, and then do it some more till you understand it. Got it? I'll see you in the next lecture where we're going to discuss the 4 major organic compounds. Thanks for watching.